Good morning, all. Welcome to today's session. And today I'm going to explain applications of Gauss's law. Last Zoom class, we have completed Gauss's law statement and its mathematical expression. And the mathematical expression is closed integral vector E dot vector ds. You can see here vector E dot vector ds equal to q by epsilon 0. Using this mathematical expression, we have to explain derivation of vector E first due to an infinite line of uniform positive charge distribution. Second one is an infinite thin plane sheet, and the third one is spherical shell. Okay, I'm going to start the first one. Derivation of expression for vector E. This is vector E. This is vector E due to an infinite line of uniform positive charge distribution. For that, we have to consider an infinite line. Here, this line is extending up to infinity, and in this line, we have uniform positive charge distribution. And to determine field intensity due to this line, we have to consider a point P, that is point P, which is at a straight separation. The separation is straight separation and is R. Straight separation R from this line. Okay, P is a point at a straight separation R from this line. To determine field intensity at point P, imagine a Gaussian cylinder. This is dotted cylinder because it is imaginary cylinder. We have to imagine a Gaussian surface, and for a line, it is cylindrical surface. And point P lies over the curved surface area of this imaginary cylinder. Okay, and we have to apply Gauss's law over this Gaussian surface. Here it is Gaussian cylinder. Okay, applying Gauss's law, and that explanation is given here. Consider an infinite line of uniform positive charge distribution and all given in this section. You can see when you apply this Gauss's law over this imaginary cylinder, we have LHS equal to integral over closed integral. Here we have to write closed integral vector E dot ds is equal to q by epsilon 0. Here you have to write closed integral. Closed notation is here. Okay, closed notation. Closed integral vector E dot vector ds equal to q by epsilon 0. And LHS of this relation is this, and RHS is q by epsilon 0. When you apply LHS over this imaginary cylinder, you can explain LHS as the sum of three line integrals. Integral over the first surface. Surface integrals, not line integrals. Surface integral over the first surface, vector E dot ds. First surface is this one. First cross section of cylinder. Second one, integral over the second surface, vector E dot ds. Second surface is lower cross section of this imaginary cylinder. And third one is integral over the third surface, that is curved surface area, vector E dot vector ds. When you add these three, we get the entire Gaussian cylinder and LHS over this Gaussian cylinder. Okay, and we have to find separately these values. First one, integral vector E dot vector ds over the first surface. Over the first surface, vector E is parallel to the surface, and vector ds is acting along the direction of n cap, unit vector n cap. Okay, angle between vector D and vector ds, that is vector E and n cap, is 90 degree. When you substitute that value here, vector E dot vector ds becomes integral E ds cos 0, cos 90. Cos 90 is 0 and the value becomes 0. Okay. Similarly, when you apply integral over the second surface, that is second part of the relation, integral vector E dot ds over the second surface, that relation becomes E ds, integral E ds cos 90. Here also vector E is parallel to the surface, lying on the surface, and vector ds or n cap perpendicular to the surface. Angle between that two is 90 degree. The second term also reduces to 0. And third part of relation, integral vector E dot vector ds over the third surface, curved surface. Over the curved surface, vector E and n cap are writing along the same line, same direction. Therefore, angle between vector E and n cap or vector ds is equal to 0. When you substitute that condition here or value here, integral over the third surface E ds cos 0 and is E ds, we have to determine E, take it outside. E into integral ds is equal to E into integral ds over the curved surface is curved surface area. It is 2 pi RL. The relation becomes E into 2 pi RL. Then you can substitute these three values, equation 3, equation 4 and equation 5 in our equation 2. And our LHS becomes first two values 0 and we have only third value, LHS equal to E into 2 pi RL. Let it be equation 6. Next, we have to determine charge enclosed by this cylinder. According to Gauss's law, flux equal to Q by epsilon 0. We need to determine the value of Q, charge enclosed by this imaginary cylinder. That is equal to Q taken as Q, and Q is equal to lambda into length of cylinder. Lambda is linear charge density because it is line charge distribution. Therefore, lambda into length of cylinder gives charge enclosed by the cylinder. Okay. Represent it as equation 7. Substitute equation 6 and 7 in our equation 1, Gauss's law, mathematical form. You can write E into 2 pi RL, LHS, equal to RHS, Q by epsilon 0, lambda L by epsilon 0. Simplifying, E becomes, L and L cancels, E becomes lambda by 2 pi epsilon 0 R. Or in vector notation, the relation becomes vector E equal to lambda by 2 pi epsilon 0 R into n cap. Hope it is understood. I am continuing